Luke Sheneman, Director of RCDS, here to talk about multimodal AI, the ever-present march of progress towards our AI overlords.
Hmm.
So
yeah. Thanks.
good for a finals week reprieve, and take it away.
Okay, thanks. So I'm Luke Sheneman, Director of Research Computing and Data Services here at the university. I'm going to give a presentation today about multimodal AI, which I'm really excited about. I gave a really similar presentation back in October as part of the IIDS, or Institute for Interdisciplinary Data Sciences AI literacy series. So this will be, if you've attended that, it's probably really similar or almost identical, but hopefully we've got stuff to learn. So multimodal AI is super interesting, and it's kind of predominating in the news right now, right? So back in October, when I gave this original presentation, there was a whole bunch of interesting news that was happening. In particular, Anthropic, which makes the Claude large language model, introduced this new tool that allows their model to control your computer. And the way it does it is by using multimodal technology to basically take lots of pictures of your screen, figure out where the cursor is, figure out where the text is, and be able to manipulate it. And in order to do that, it has to understand in a deep way what it is it's looking at, and combine the images that it gets from the computer with its understanding of text, of language. And so in that way, it's multimodal. I've been playing around a lot with interesting multimodal models that are generative, that generate things like images. And so this is right here. You have a picture of my boss, Barry, who's the director of IODS. I took his image, just a still image off of the web, and I was able to send it to a model called Minimax that was able to take his image plus a text prompt and animate it. So it was a text to video model. And because it combines text and another mode, it is considered multimodal. And then on the right-hand side, you can see something similar where they took, the famous picture of the girl with the pearl earring and animated it in a very lifelike way. And again, that's also with the Minimax model. So my favorite is, of course, Barry, my boss, high-fiving Sam Altman from OpenAI, a bunch of times. So these are examples of some of this stuff that has been coming up recently. And one of the things especially about the Anthropic situation, where they have this computer control method, reminded me of this really awesome meme from, I don't know, a few years ago, right? This Alex Bleckman said, it's a joke, right? So, sci-fi author, in my book, I invented the torment nexus as a cautionary tale, right? And then some number of years later, as tech geeks do their thing, the tech company says, at long last, we have created the torment nexus from the classic sci-fi novel, Don't Create the Torment Nexus. And so it's like, we've read and seen a lot of interesting sci-fi about how AI systems can take over computers and sometimes do malevolent things. And it just seems like we're creeping that way, right? So kind of like you were saying about AI overlords, right? So it's just kind of a funny joke, but multimodality, which I'm going to talk about a lot in this talk, is central to that. Right, because in order for AI models to do important things in our world, they have to understand the modes in which humans interact with our world. And so I'm going to talk a lot about generative AI. So when you talk about multimodality, you don't have to talk about generative AI, but generative AI is, in a lot of cases, multimodal, right? And you can see like OpenAI Sora, the text-to-video model, where you can input a simple prompt and get up to a minute of 4K video at 30 frames a second, right? And it's incredibly coherent, right? And it's the lighting, the characters, the ability for the model to actually deal with things like occlusion, where something is hidden for a while in some frames and then appears again naturally, in subsequent frames. All of that is pretty impressive, and that's an example of generative AI. It's a generative multimodal model where it takes as input text and outputs on a different modality, in this case, video. Obviously, large language models are generative. They're able to generate natural language based on prompts. They are increasingly multimodal, and I'll talk a little bit about that, or a lot about that. We've got things like Midjourney and Stable Diffusion and Flux and other systems that can generate just images from text. You can create music. You can create, voices from text. Going from one modality like text to another modality like images and video. And then there's this. You can also use multimodality in science, right? And so AlphaFold. By the way, the winner of the Nobel Prize in chemistry this year were the people from Google DeepMind who invented AlphaFold. AlphaFold is a system that takes as input amino acid sequences and produces as output three-dimensional protein structures. Okay, and this is a problem that biologists have been working on for a long time. Back when I did my PhD in bioinformatics, this was a hot area. It's almost a solved problem now, and it's because of these generative large models like AlphaFold, which is multimodal in the sense that it takes as input amino acids and it outputs a three-dimensional structure. And again, these a lot of the AI stuff that especially generative AI stuff that we see in the news is about creating content or creating images or video or text or music or whatever, but they're being used increasingly for hardcore science. AlphaFold is just one example. So let's define some terms here, right? So unimodal is when you have a model, an AI model of some sort of large, like a large language model that takes as input text and outputs text. Okay, that's one modality all the way through, right? Input and outputs all text. You can do the same thing with images. There is an upsampling model called SRGAN, which stands for Super Resolution Generative Adversarial Network. And it takes as input a small image, and it produces a high quality, really well rendered large image, right? It fills in all the gaps and it makes it look really smooth. It's not pixelated, right? And that's an example of a unimodal AI model. One mode in, one mode out, the same mode out. You can have pseudo multimodal models. And so like GPT-4 was like this, right? Where it took as input text. It's GPT-4, and I'm not talking about 4.0, I'm talking about GPT-4 from OpenAI was a text-to-text model, right? It would take as input text, it would output text. But you could combine that with other models. For example, a model that could take an image and convert it into a caption and then feed it into GPT-4. Or a speech-to-text model like Whisper, which is one of the OpenAI models where you can talk, it will convert that to text and then send it to the model. And then as output, be able to send it to a generative model like DALL-E to take text as a caption and produce an image, or TTS, which is their text-to-speech model. So it would kind of behave as an ensemble of models to provide some sort of coherent multimodality. But then there's native multimodal models, right? Where you input one thing like text and you get as output something else like an image or a video. So text to image would be one way, and the reverse of that would be like image captioning. But the frontier right now, what's really interesting and what all the big AI companies are working on are native multimodality with lots of modalities, right? Where they can input all sorts of different modes like images, video, text, speech, music, whatever. They can input that, have a common understanding of what the content of those things is, and then be able to output in similar, into a variety of modalities, right? Whether it be generating images like DALL-E or like Sora, video like Sora or whatever, but doing it not as an ensemble of different models, but as one unified single model that understands how to take all of that as input understand the relationships and the content of what's in those different modalities, put it into a sort of a unified latent space uh, or semantic understanding of all of that, and then be able to emit that into modalities that we can understand. Okay, so like the current frontier models, like the big cloud uh, hosted models right now, like GPT-4o, Claude 3.5, Gemini Pro, all of those can handle multimodality at this point, and even Llama 3.2, which just came out not too long ago, now can also do text and images, and it's open weights, open source. Gemini Pro from Google is probably currently still the best at multimodality because it actually natively handles video. OpenAI can handle, they say they can handle video, but what they're really doing is taking frames and then, at a certain frequency and looking at them as still images. But with Gemini Pro, you can actually like analyze a video. You can ask it when in this video did this event happen, and it will be able to tell you because it understands what's in the video, which is super impressive. But this multimodality is increasingly important for these companies and for the users that use these tools, and I'll explain a little bit why. But you don't have to be generative to be multimodal, right? And so generative means, of course, that you're outputting in some mode that humans can consume, right? Whether that's text or images or video or music or whatever. That's generative AI. But you can use multimodality to do sort of traditional sort of predictive modeling with AI models. So in healthcare in particular, there's a lot of papers that have come out in the last couple of years, especially this year, about multimodality in healthcare. And so the example from this paper, which came out this year, the Integrated Multimodal Artificial Intelligence Framework for Healthcare Applications, uses it's got a mechanism by which they can take different data modalities, whether that's tabular data, about a patient's test results or, attach sensors to them of some sort to understand their blood pressure and whatever. That could be tabular data. You could take time series data, so like how that patient is behaving over time. Natural language, so notes from a patient visit or a list of symptoms or doctor notes or whatever could be represented in natural language. And then medical images. So you could have X-rays and MRIs and CAT scans and whatever, sonograms and things like that. All of these different interactions in the healthcare system and with healthcare providers can take these different shapes, these different modes. So what this paper did was basically encode all of those into a common embedding space, into a common multimodal embedding space, which then they can reason and predict outcomes or provide guidance to the patient about X, Y, or Z. But it's this AI model, and it's not generative in the sense that it's not generating an image, it's maybe not generating text, it's generating instead predictions about healthcare outcomes. So again, multimodality does not require the use of generative AI. And multimodal models outperform unimodal models. And so it's been proven and demonstrated time and time again that multimodal models will do a better job than single modal models or unimodal models. And that's because they're able to integrate different data types. And because they're able to do that, they have a richer semantic representation internally of objects that it takes as input. And it's able to leverage complementary data across modalities to fill in gaps. So for example, you might have a text description of something, but it might be missing some key details, but you provide along with it a picture, and then that fills in the gaps, right? And maybe you provide some audio, and that also fills in the gaps. And so you end up with this richer semantic, soup of data that helps the model actually do better. And really, you're just training these large models now on a lot more data. It's also kind of similar to how humans learn. Like, there's no human in the world that learned just from text, right? That we've learned from our senses, from different modalities, and now these models are able to do the same thing. one of the reasons why I think the large companies are so interested in multimodality too is just because they've trained already on pretty much everything ever written. They've run out of text tokens to train on. So now they're turning to video and audio and music and those kinds of modalities for additional data. And I think in the future, you're going to see with robotics, especially, you're going to see robots that are able to collect a lot of data, um, novel data through interaction with the world, right? And all of that's going to be this constant data stream that we can collect, harvest, and train these models to do ever greater things and to develop really a sophisticated sort of world model or understanding of how things happen and interact in the world that goes beyond what's possible with just text. Um, okay, so I'm going to give just a little bit of a technical primer here. And by the way, all these images that I presented here, I generated with a multimodal model, a text-to-image model called Flux. It's an open weights generative text-to-image model that does a really good job. So, so neural network basics. So these multimodal models are neural networks. They use neural networks under the hood. Okay, so what is a neural network? Just really, really quickly. A neural network is what you see represented sort of at the top here, right? So you have a bunch of nodes. Those are the circles, and those are often called neurons. Okay, so those are neurons. The neurons are connected to other neurons with edges, and those are the lines that you see connecting the neurons. This is an attempt. This methodology of creating this neural network was, by the way, is sort of based on our understanding of how the actual nervous system and the brain works. And so, where we have neurons, we have connections between the neurons, and the connections between those neurons get strengthened or weakened as we learn things. And so that's very much what's happening here. And in this case, you can see that the network itself is organized into layers. You have an input layer and an output layer, and in the middle you have some number of hidden layers. And this is another name for this kind of network is a fully connected neural network, and it's fully connected in the sense that every neuron is connected to all the neurons in the prior layer and all the neurons in the subsequent layer. And every edge, the thing that connects the neurons, has associated with it what we call a weight. Okay, a weight is just a parameter. It's a trainable parameter. And so every edge has a weight, and then every neuron has another trainable parameter that we call a bias. And so if you look down here at the in this lower left section, you see that we've got two neurons that are connected to X1 and X2 that are ultimately connected to a neuron Y. The neurons, each connection has a weight, so weight 1 and weight 2, and then Y has another trainable parameter that we call a bias. And so what we do when we're trying to train one of these models is we pass our data into the input layer all the way through, we do a forward pass through the fully connected network. And then we evaluate what happens on the output layer. We'll get some responses. In this case, we just have one neuron on the output layer. It's probably a binary classifier or something like that. And then we just, let's just say that we're asking, is this a picture of a dog? Yeah, yes or no? Okay, in this particular network. And then we, and the input are the pixels of our image. And what we do is we pass our data through, we look at the prediction that comes out on the output layer, and we compare it to the labels in our training set. So we have actual real labels, supervised labels with our training data. And that we can say, okay, this really is a dog. That was a correct prediction. Let's make sure that we tune our weights and biases. We go backwards through a process called backpropagation, and we optimize that through an optimization strategy called gradient descent. Gradient descent is this way of sort of traversing a loss landscape to optimize the parameters of our model. It's a mathematical sort of algorithmic approach to optimization of our parameters in our model. And the thing is that the model itself, in order for gradient descent to work, has to be differentiable, which means you have to be able to take the derivative of the parts of the model at every point. So as long as you can do that, you can use gradient descent, and you can optimize iteratively by passing your data through the model repeatedly tweaking those knobs and dials through gradient descent, you can improve and learn from your data, right? And the thing is that those hidden layers in the middle serve a role. They're organized in layers. You have the first hidden layer sort of starts to aggregate very basic rudimentary features. So in this particular case, we might be doing like a facial recognition algorithm, for example, or a network. And so we pass into our input layer our image, and then by this first hidden layer, we start aggregating really basic things, features like edges or light spots and dark spots. So really very simple, basic features from our data. Then, as we take that input layer, that hidden layer becomes the input to the next hidden layer. So now we're starting to aggregate those features, the extracted edges and light spots and dark spots, and maybe into things like ears and eyes and nose, these discrete facial parts of faces. And then by the last hidden layer, maybe we're starting to aggregate things into sort of more complex facial structures, and ultimately able to do it like a facial recognition neural network, for example. But that sort of cascading effect of sort of handling ever more sophisticated, complicated, aggregate, composite features is an important part of how neural networks work. And then there's two different modes to dealing with neural networks, right? There's training and inference. Training is just where you pass a lot of data through your network, like I described with the gradient descent, and you tune your knobs and dials, your weights and biases to get a network that is optimized for your particular task, whatever that task is. Again, you're trying to traverse this loss landscape. You're trying to reduce your loss. So the loss is the difference between your predictive label and the real label, right? So you reduce your loss until you get to some stopping point. Either you run out of time, or the model works really well, or whatever, you stop, and then now you have a trained model, and it's static, it's trained. Then you can use it for new data. You pass it new data it's never seen to be able to use it for whatever task it is that you were trying to use it for. And that's called inference. So you have training and inference. And so with generative AI, really what you have, one of the ways I like to describe it, right, is that when you're training it with labeled training data, or sometimes these models are self-supervised or unsupervised, but they're ultimately trying to understand the distribution of your data, right? The statistical distribution of your data, which can be very highly dimensional, right? It's not just a couple of dimensions. The data, depending on what it is you're feeding it, can be highly dimensional, thousands, hundreds of thousands of dimensions potentially. And then once you have that complex data distribution, then you can sample from it. When you sample from it, once you've learned, for example, how to generate it, what an image is of a certain type, you can sample from that to create an image, or you can sample from it to create, predict the next token with a large language model. And so that's what you're seeing here. And on the bottom here, if we have a system that learns the distribution, the statistical distribution of what a human face is, then once you have that, you can sample from that to generate unique human faces that don't really exist in the real world, but come from your distribution, right? And we do that with models like diffusion models, which I'll talk about in a minute. Or in the case of large language models, you sample from your distribution to pick the next most probable token for large language models. And so in a lot of ways, when you're creating that highly dimensional statistical distribution of your, the representation of your training data, the model itself isn't as big as your training data, so you have to compress it. It's a compressed representation, right? And in a lot of ways, machine learning AI, it's about data compression. You're compressing your training data by finding all the most important salient features of that and storing it in this compressed distribution. This we call it either a latent representation, or we'll call it embedding space, and I'll explain what that means in a minute. But it's this compressed representation, and then from that you uncompress it using so you encode it into that compressed representation with what's called an encoder, and then you decompress it or uncompress it using a decoder into again, a modality that humans can consume, whether it's images, text, video, audio, whatever. There cannot be generative AI without a decoder. You have to be able to decode that compressed representation back out into a mode or a data format that humans can consume, whether it's natural language or images or what. And in fact, some generative models, for example, like GPT-4, for example, is what's known as a decoder-only neural network or transformer network, because once it learns its initial encodings in pre-training, then when you use it at inference, there's no more encoding, it just decodes. And so, but the decoder is essential for generative AI. Okay, so I'm going to talk a little bit about the transformer architecture. So this is a neural network architecture, a particular sort of way of organizing neural networks to do things that has enabled all of the most powerful AI that we have today, right? So it's been super transformative to transform, but in modern AI. So all of the latest large language models and almost all of the generative AI models that are used today are based on this transformer architecture. And it was introduced in 2017 in a paper that Google published called Attention is All You Need. And that paper really changed the landscape of artificial intelligence research, across the board. And in this particular paper, they were trying to do something relatively modest, which they were doing a language translation between, I think, English and German and English and French, or it's the other way around. But they were looking at a translation exercise of natural language. And they developed this transformer architecture, which I'll go into more detail on. And it did really well. And people started adopting it for lots of other things and found that it did really, really well on lots of things. And so I don't think they really understood the impact that they were going to have when they wrote this paper, but it's been profound. And so why is it called a transformer? Okay, so a transformer works like this, right? So you have your initial, I'm doing it in language, and I'll go back to images and stuff in a minute, but it's easier to kind of describe it in language. It's called a transformer because you start with your inputs, right? And in this particular case, we have a set of words, and we compute what are called embeddings from those words. And I'll talk more about what those embeddings are. It's really essential for modern AI. But you have your words, you calculate the embeddings for that, which is really an encoded representation of that word. And then you transform it. So you use a mechanism called self-attention and some fully connected neural networks to transform the embedding, which is the semantic meaning or the representation of that word. You transform it into another representation of that word in which the context of your overall sequence is considered. So the word the, for example, the embedding for that is going to pass through the transformer, and it will be transformed into a different representation that takes into account all of the other words in your sequence, your input sequence. Also in context of all the stuff that it learned during pre-training from learning everything about all the words in the world, right? So it used that plus the current context to transform your word into your embedding into something else. So that's why it's called a transformer. It's transforming your embeddings. And one of the properties they found pretty early on, and I think OpenAI and Google both identified this pretty quickly, was what they call the transformer scaling laws, which is to say that these models based on transformers, they improve predictably as a function of the amount of data you give it as input and the amount of compute that you apply to it. And so the amount of compute is really the size of your network, the number of weights, the number of parameters in your model, but it's also like how many times did you evaluate your data? How many times did you run your data through it? It's a general kind of term, but these here on the diagram, you can see that the y-axis is your loss. And again, you're trying to optimize your loss. You're trying to lower your loss. And that loss gets reduced predictably with transformers as you increase your compute and your data. And that's different from a lot of other conventional neural networks, which would often, almost always, plateau, right? You get to a point where adding more data didn't help, increasing the size of your network wouldn't help. They would plateau at some point, and nothing you did would make them any better. They just reached some sort of intrinsic limit. But the thing with transformers is they seem to obey these scaling laws, which is as you add more data, you add more compute, they get better and better and better. And so that's why the current model, the current data centers that are training these things are huge, right? Like vast data centers with hundreds of thousands of GPUs, working for months to try to compute the next iteration of GPT, for example, or Gemini or whatever. And in fact, just a couple of days ago, Elon Musk announced that they were going to increase. They already had, I think, the largest GPU cluster at 100,000 GPUs for XAI. He just declared they were going to expand that to 1 million GPUs, right? Like they're spending hundreds of billions of dollars. Our power grid can't even sustain like the amount of data centers that are getting put up. So companies like Microsoft and others are starting to reboot nuclear reactors just because of these transformer laws, right? These transformer laws are creating an enormous impact on everything. I should say it's not a law in the sense that it's not like a natural law. It's more like Moore's law, right? Like it's like a property that was sort of discovered, but it's not like a natural law. So at some point they'll reach some limit somewhere. But so far it seems like adding more compute and adding more data makes these models better and better and better. And now you're starting to see scaling laws on the inference side. This is for training, right? But on the inference side, they're starting to spend more compute on the inference side and getting better and better results. And so think models like O1, for example, from GPT will do that. Okay, so the thing about transformer models is that they can only work on sequential data. You have to give it a sequence. You can't give it just an image. It has to be a sequence. You can't just give it a video. It has to be turned into something serialized. And I'll talk a lot about that because that's important when we start talking about multimodality. And then there's this whole paradigm of that they either introduced or sort of enhanced, which is called attention. And I'll go into some detail about attention. But the other thing about transformer models that made it different from previous models is that even though these models are huge and take lots of compute, they can be parallelized, right? So you can parallelize the training and inference on these models to a significant degree, which means that you can have models much larger than you ever could before. And so, a large language model based on transformers, they're just functions. You remember I said, in order for a neural network to apply gradient descent, it has to be a function and it has to be differentiable. So it's literally just a differentiable function. It takes as input a series of n tokens. A token can be like a word. We'll just think of it as a word. It takes a series of n words, and it just outputs one token. That's all it does. It's a function, takes an input, and it produces one token as output. So for example, if I input into a transformer-based large language model, the robots want to eat, that's my input sequence, then it's going to, that's f of x, right? It's going to respond and it might predict the word me. The robots want to eat me. Okay, so that's all it does is it predicts that. And so when you're using these large AI models like from OpenAI or Gemini or Claude, and you're doing it through like programmatically through their API, you have to pay by the token. And really what you're doing is you're paying for how many times you call this function. Because every time you call the function, you get a new token, right? And there's, it depends on how many input tokens you have as well. But it's an expensive operation, so they have to recover their costs for you running this function. But the way that the transformer models work is that they're autoregressive, right? So they just basically take that function and put it in a loop. And they just say, okay, well, I'm going to look at your current sequence. That's your input. I predict the very next token. I take that next token and I add it to my input sequence. So now my input sequence is one token bigger. And then I run it through the whole model one more time. And then I get another token, and then I put it in my input sequence. And you do that repeatedly until either the model, until you hit some sort of like limit of how many tokens you're allowed to output, or the model can emit a special token, which just means stop, right? It's a stop token. Like, the response to this prompt is done. I don't need to go any further. And so, and that's all it is. It's autoregressive, calling this function repeatedly over and over again. And it's super mechanistic and simple. But the result, because these things have such a nuanced understanding of language, is still really powerful. Okay, so I mentioned embeddings, and embeddings are absolutely critical for modern AI, especially for multimodal models, but also just language models. So in the language model case, what you do is you take your token, we'll just say it's a word, right? Like the word the or to or whatever. It has a number associated with it, right? Your token, you have a fixed dictionary size, right? And most of these models like GPT use a dictionary size of 50,000 subwords, but each token has a single integer number that associates with it. It's just an index. And then you calculate, an embedding. An embedding is just a list of floating point numbers. It's a vector, right? It's a vector of numbers. In this case, I'm just showing three floating point numbers. In the case of GPT-3, this is, I think, 12,288 numbers long, floating point numbers long. Each one of these positions represents a dimension in your vector, right? So you have this highly dimensional space. GPT-3 had like I said, over 12,000 dimensions. But what that token represents is the semantic meaning. That token embedding represents the semantic meaning of your token as learned during pre-training of your model by looking at the whole corpus of data and where that token is used with other tokens, right? The statistical co-occurrence of that token with other tokens in various contexts. And from that, it's able to extract this semantic understanding, this vector. And so if you look at it just in two dimensions, this will kind of highlight how this works, right? So say, for example, you had an explicit two dimensions of age along the y-axis and gender along the x-axis. You can see that like child and infant, as far as gender is neutral and age, it's young, right? And so they're close together in that two-dimensional space, right? Not only that, but the angle between the vectors, and you can think of the vectors like in physics where they have a direction and an amplitude or a magnitude. There's an angle between child and infant, right? And it's relatively small. But the difference between, say, girl and grandfather is very huge on this two-dimensional graph, right? That's a large angle. And the thing is, you can calculate that angle from vectors using a linear algebra method called dot product, right? A dot product is a way of calculating the angle. You can use it to calculate the angle between two vectors, and a vector is just a series of numbers in a high dimensional space. So you can use dot products. And so dot products are kind of one of the key linear algebra functions that transformers use inside the hood. Okay. So remember when I did the facial recognition example where we had a bunch of hidden layers and each hidden layer did more and more composite and aggregate features? Transformers do exactly the same thing. So in the first, you have a bunch of layers, transformer layers, and they're basically entire transformer submodels inside the overall transformer. And each one of them handles an ever more complex, nuanced understanding of language. So your first transformer layer might pick up on very basic things, like this is the subject and verb of this sentence. Then the next transformer in the series of transformer layers in an overall larger transformer model uses that as the basis for its decisions on how to eventually transform your embeddings. So you get this incredibly, by the end of say 100 transformer layers, you end up understanding humor and sarcasm and idioms and all this other stuff with natural language, right? But it's based on learning these basic things in natural language and then getting better at it. And the thing is that you know, ultimately, if you're trying to predict the next token, given, say, a sequence like this, what you're trying to do is you just look at the embedding from the very last token, right? Because you're predicting, say your task is next token prediction. This embedding here should be predicting the next token in the sequence. And every word in your dictionary is given a probability. And you just pick the one that has the highest probability. So in this case, where we say the fish lived in the next one, you have a bunch of, after you transform it all, with the transformer model, you'll be able to look at your probabilities for that next token, and you just pick the highest one. So the fish lived in the sea would be the most probable one. You can increase the temperature of your model a little bit, which is just a hyperparameter for your model. And then you can pick one of these other words at some frequency. It's not the optimal, most probable one, but it's not bad. So the fish lived in the blue might be okay, right? And so if your temperature is increased a little bit, that's essentially what it does. And that allows the model to be a little bit more stochastic, a little bit more creative, and give you outputs that are different every time. And that's going to be important in a number of ways in multimodality. So again, self-attention works by every token looking at every other token, and really you're looking at token embeddings, right? So you're comparing embeddings between all the tokens. I'm gonna, in the interest of time, gonna kind of skip ahead here. So I've talked a lot about language, and the reason why I did that is because it all applies now to images and audio and other modalities. But let's look at this particular case of multimodal vision, which is images and text, right? So in that particular case, if you can create a multimodal model where you have an understanding of both images and text, a mutual understanding, then you can do all sorts of cool things, right? You can do image to text matching. So given a prompt, find the image that matches that, or given an image, find a reasonable prompt that matches that. You can do image captioning. So given an image, describe it in natural language. Give me a full description of what's in that image. You can do visual question and answering. What is so and so holding? What color is the sky? You can ask natural language questions of an image and get an answer back. You can do sentiment analysis, understand emotions of people, that sort of thing. So sentiment analysis is relatively straightforward. Again, this is my boss. It's a modified version of him. He doesn't really look like that. I said, okay, well, what's this person feeling? And this is GPT-4o, I think. And it just went into great detail. I had to cut it off like pretty early because it was just so long, but it was like a really nuanced, detailed understanding of exactly what kinds of emotions this person is likely feeling, right? Because it was trained on enough data where emotions and images of people were sort of described thoroughly, right? And I'll talk more about that in a second. So you can get sort of sentiment analysis, image captioning. So given a scene, it's an artificial scene, just let it sort of describe it. And it doesn't just describe like technical details of it, but it will describe the mood and probably the emotions that the people are feeling and all this other stuff, right? Because it was trained on really rich training data. And then you can do question and answer, like what's on the table, where are they? And, that would be an example of question and answer. So how does this work? So one of the cool models that you probably never heard of that is behind the scenes on a lot of this stuff is called CLIP. And CLIP stands for Contrastive Language Image Pre-training. It's a model that came out, I think, 2020 or 2021 or something like that. And what they did was they trained a model given, it was 400 million images and associated captions. So 400 million images, 400 million associated captions. And what they did was relatively straightforward, but they calculated the embeddings for the text, right? They calculated the embeddings for the image, and I'll talk more about how you do that. And they just made sure that for images and captions, that those embeddings lined up, right? So they basically rewarded uh, the model when it calculated embeddings for images and their associated captions when they were together. It made sure that those embeddings were the same. And if you had an image and a caption that wasn't related to that image, that those would be far apart, right? And so it's contrasted in that way. And so ultimately, you ended up with this in what we call an embedding space or a latent space, in which images and their associated captions are located in that embedding space in a similar place. And once you have that shared embedding space, then you can do all the things I just described, right? You can ask it to generate captions, you can do questions and answers and things like that. And again, it used things like dot products to make sure, like, to calculate the angles between the image embeddings and the caption embeddings to make sure that the dot product, the angle was minimized between the two. Okay, but wait, so I mentioned earlier on that transformers can only work on sequences, right? And an image isn't a sequence. In 2021, Google DeepMind came up with this paper, an image is worth 16 by 16 words, transformers for image recognition at scale. And what they did was they applied transformers, which usually were used for large language models, they applied it to images. And the way they did that was to take an image and carve it up into little patches. And so these patches, in their case, and in most cases, a typical patch size is 16 pixels by 16 pixels. So it's a relatively small little patch of the image. You carve it up into these patches, and then you serialize that. You just turn it into a long sequence. So now you have a sequence of patches, these small patches. And you can think of the patches as tokens. So they work almost exactly the same way as a token. And again, what we do in a large language model is we take a token and compute its embedding, right? You do the same thing with these patches. So assume you had an image that's 512 by 512 pixels, and you carve it up into a bunch of 16 pixel by 16 pixel patches. You end up with a sequence of length 1024, which is, a reasonable size for a transformer model. But the trick here, though, is that, like in large language models, we have a fixed vocabulary size. Tokens are discrete, words are discrete. We had 50,000 tokens, subword tokens in our model. And for each one of those, we can have an embedding vector. And so it's this two-dimensional matrix, which is basically the number of tokens by your embedding length, right? That's your embedding layer. But in case of images, a 16 by 16 red, green, blue patch has some crazy amount of possible outcomes, right? It's actually 2 to the 6,144, which is like a crazy number. And so you can't have a vocabulary, a discrete static vocabulary. So what you do instead is you create what they call a linear, or sometimes it's nonlinear projection, which is really just a function that you learn. It's a neural network, which is a way of approximating a function. You learn this function, which can take a serialized version of a patch and convert it into a long patch embedding. Okay, so this function can take any arbitrary patch and turn it into an embedding that closely matches without having to have a discrete mapping of token to embedding. It's a continuous embedding. So it's just a function, and it's a function implemented as a small neural network. So then what you can do is you can take your image, you can serialize it, you use your linear projection to turn that into an embedding, and now you have a series of embeddings. Once you have a series of embeddings, you can do transformer stuff with them, right? They're just embeddings. The key thing to note, though, is that images have two-dimensional spatial characteristics, right? There's an X and a Y. And so you have to encode what's called positional encodings. You have to encode where that patch came from the image, like XY, right? There's ways to do that. I'm not going to go into the details there, but that's also included as part of the signal, so that it knows not only these patches are part of your sequence, but in the overall picture, this is how they were related to each other, XY. Okay. Now you can start doing really cool stuff. You can do stuff like image in painting and out painting. This is a case of out painting. I don't know if you guys have ever seen this particular picture, but it's where they took this original very famous painting, and they applied out painting to it, which is what they did, not next token prediction, but next patch prediction, to basically draw the scene, like basically zoom out, have a generative AI model paint the rest of the scene in the style and in the content and semantic, uh, you know, sort of coherence to the original image. And so you end up with something like this, which looks great. It was, I mean, it's, who knows, but it's like came out of nowhere, right? But you're basically doing next patch prediction as you zoom out. So make sure I have enough time. So I did a series of talks last year, and one of them was on vision transformers, where I went into a lot of detail, like exactly how to carve things up and apply transformers to images. And so I've got a GitHub repository for that. I should have a QR code so you guys can take pictures of it. But if you look on my GitHub, you can find more information on that. So how do we transform now? So if we want a model that can understand both text and images, how do we do that, right? So we talked about clip, and clip's kind of key to it's a good hint on how to do it, right? But what you need is you need to be able to take a series of text tokens, like a description, and you need to be able to take an image, and you need to be able to encode those into the compressed latent representation, the embeddings for those tokens. Then you can apply self-attention through the transformer mechanism to get a transformed set of text tokens, just looking at each modality independently. So I take my text prompt, convert it to embeddings. I kind of try to figure out within that modality what it is I'm looking at by applying transformers to it. And I get a set of transformed embeddings. I do the same thing for the image, just how I carved it up into patches, and you end up with a set of embeddings. And then you apply what's called cross-attention. So cross-attention is a mechanism by which it applies attention, but all the tokens in the image can look at all the tokens in the text, and vice versa. They're providing cross-attention. You're actually looking at the semantic distance between the words and the image patches, right? And you apply that cross-attention until you develop this shared embedding space where the images and the text reside in a common understanding in the model from the images and the text. And so that's great. And you can do all of that if you just have descriptive enough, long enough captions of images, but you can go beyond that, right? So if I generated this image using Flux of Joe Vandal with a lightsaber, right? And you could have a much larger caption, which describes a lot of the scene, right? More of the detail of the scene. And you should have a much more detailed caption than that if you're trying to train a model. But you can also go further than that and do things like segment the image, find all of the individual discrete parts of the image, and find the pixels that correspond to that particular thing. So in this case, the lightsaber has a color, the glove has a different color, that they have different labels for those different discrete parts, right? That's called segmentation. Or you can do something related, which is just draw bounding boxes, crude bounding boxes around objects, right? And give them a label. So similar things. You can generate a scene graph, which is like how things are related to each other. I'll talk a little bit more about that in a second. Or a set of questions and answers, that are in that form that you can attach as you train the model. So a scene graph is really simple. So you take something like this where you have the bounding boxes around discrete components within an image, discrete objects. And then you basically just create a graph that describes how they're related. So in this particular case, the woman has a helmet, the woman has a boot, right? There's nodes and edges. The nodes represent objects, the edges represent relationships. You can do that for entire scenes, and this is often used for things like video games and stuff like that. But it really is a way of developing an understanding of what's going on within the picture. So the thing is, you can represent all of these labels just as JSON. You can represent the caption, the bounding boxes, the segmentation maps, the scene graphs, and you can provide that as additional input to your model when you're training it. So not only does it have a textual description in the caption, but it has this deeper understanding of where everything is in the image and how they're related to each other and what's what and all of that. And the trick there though is that that could be really time consuming, right? To go through and label an image, everything in an image. That's just one image, you have to, these days you'd have to label billions of images. So, but we're at the point now where we can bootstrap that process, right? We have AI models that are often very specialized that can do all of these things for us. Given an image, give us a caption, find the bounding boxes, let's do a segmentation. So I think that a lot of the computing that goes into training models these days is not so much into actually training the neural network. It's just getting the labeled training data into the right format with all of the detailed, nuanced training labels that you need in order to really create the best possible model. So a lot of emphasis these days is not so much on model architecture and spending time on that, although that's super important. It's on the getting the data rich and well labeled and spending a lot of time on that. Okay, so in the interest of time, just to wrap up, I did want to talk about diffusion because it's super cool. And this is how models now generate things like images, video, music. They use this method called diffusion. And it's actually really cool. So the idea is that you have basically forward diffusion and reverse diffusion. And in the forward diffusion paths, what you do is you take an image. In this case, it's an image of a cat, right? And you degrade the image by adding a little bit of Gaussian noise, or just normally distributed noise, just a little bit. And then a little bit more and a little bit more until you get to this point where it's just completely random. But at each phase, at each step, you train a neural network to denoise it, to return it from the noisy state to the previous state. And you train this network so it's a really good denoiser, right? It knows how to go from noise to something that has more signal. And so what you do in the reverse diffusion process is you pass it just pure random noise, just garbage, right? Just pure static. And then you have it denoise it incrementally until you get out of it something that it learns, based on the distribution, the data distribution that you have. You just incrementally denoise it. But the cool thing is you can do that you can condition your denoising based on other modalities like text prompts. So that's how text to image works, right? You give it a prompt, and as it's doing the reverse diffusion process, it's basically computed the embeddings for your text prompt, and each step along the way, as it's denoising the image, it makes sure that the embeddings from the image embeddings from the denoised image are in alignment with your embeddings for your text. Again, it's sort of like how clip is used. In fact, I think the original version of DALL-E, or maybe it was DALL-E 2, was called unclip, right? Because they use this idea of having common embeddings for images and text, and then being able to use that to guide a reverse diffusion process to provide, at the end of it, an image that looks like something from its data distribution, but also conditioned on your text prompt. And because of that, you can end up with all sorts of unique things that have never been seen before, that are some sort of strange combination of stuff that it's learned in the context of the prompt that you provided it. And so that's how all of these models work. And so I created a simple diffusion, just as an experiment, a simple diffusion model that could construct human faces. And it was just an exercise, so you can see the faces aren't very good, but they're human faces. You can tell that, and I just trained it on, I think, 5,000 faces from celebrities. I didn't use text conditioning. I just taught it what a human face was, and then I would give it random noise, and it would produce this stuff, right? And if I had more data and more compute, I could have made it better, but it was kind of fun. Yeah, so I only used 5,000 images on a single GPU. Stable Diffusion, which is now a couple of years old, was trained on 600 million captioned images, and took hundreds of GPUs and almost $1 million to train. So video diffusion is the same thing, except instead of using, so if you think about video is just 3D data, right? It's images over time. And so you can encode them, you can create an embedding for patches in video. But in video, you don't just have XY patches, right? 16 by 16. Now you have time too. And so we call them space-time patches. And so if a space-time patch might be 16 pixels by 16 pixels by, say, a quarter of a second, right? So you have a space-time patch of data. You take your video, you encode it into a series of space-time patches. You serialize it, and you do the same sort of linear projection to create an embedding for that. And now you can use transformers on it. So video is actually not that hard. It's just very data hungry, right? Because it's a lot of data. And your sequences can be quite long, but it is the same concept just applied to 3 dimensions. And so you can have, generative video diffusion is almost identical to the 2D diffusion I just talked about, except it uses this 3D space-time patches. And so again, OpenAI Sora, which I think will be released soon, we'll see, uses a diffusion transformer to denoise all the frames of an entire video all at once. So it can do up to a full minute of video at 4K, 30 frames per second. But the thing is, what it does is it starts with a minute of just static video, right? Just garbage video, the whole thing, and denoises it all at once. So it's not like it denoises the first frame and then the second frame and then the third frame to make it sort of coherent frame to frame. It literally denoises the whole thing stepwise from like really noisy to like less noisy, but across all the time steps at the same time. And that's how it's able to deal with things like occlusion, where you have, say, an object going by in a scene, goes behind something, and like 20 seconds later pops out again, right? Because it's able to maintain that temporal coherence across the whole thing. And so it's super cool. And that's what, there's a lot of these coming out now. Some of them are now open weights that you can get. But they're pretty computationally intensive. And again, you can apply the same kind of advanced labeling, but now instead of labeling just an image, you've got to label at least the important keyframes within the video of what's going on and at what time step in the video and that sort of thing. But you can develop an understanding in the model of a video and text. And so one of the things that, just this thing's one of my last slides I wanted to emphasize is at the time that I gave this presentation in October, somebody was playing with that Minimax model, which is that text to video model that was freely available. And they wanted to see how well it could reproduce human emotions. And so they created a video. This is a fake person having fake emotions, right? Totally artificial, but it did a remarkably good job of understanding emotions, which means that it was trained on some pretty sophisticated labels, right, about what these different emotional states are, and was able to now generate, video that was compelling, right? And so, one of the speaking of cautionary tales, the thing that I think, just to keep our eyes on is that in another year to 5, I don't know how long, right? These models are going to be very realistic. They're going to be able to understand your emotions. They're able to express emotions themselves, even if it's just sort of from a data distribution, but in a way that's almost indistinguishable from a human, right? And when OpenAI released their sort of advanced voice features or announced them, they said, look, some people are going to get addicted to this because it's going to respond to you emotionally. You're going to develop some sort of relationship. Some people are going to develop relationships with these AI models because they seem so compelling. And in fact, there's a company called Hume that specializes in creating empathic voice models. So voice models that understand your mood and your emotional state and can respond accordingly. So who knows what that's going to do to the human psyche in the future, but super fascinating nonetheless. So anyway, yeah, I just wanted to end with that. I'm happy to answer any questions you guys have. And we, as a university, created this new website. We're still populating it, but this ai.uidaho.edu, where we're hoping to be a kind of this central place to store information about what's going on about AI on campus and classes and opportunities and events that are happening. So check that out at some point. But yeah, happy to answer any questions anybody has.
And this presentation is also recorded and will be posted on YouTube. So if you missed anything in the slides or you want to revisit it, I'll send you guys that link afterwards. But yeah, people on Zoom, feel free to put something in the chat if you're interested.
And if you don't, that's okay. Okay. All right. Well, thanks everybody.
Thank you so
Appreciate
much.
it. Yeah.